Hello, I'm Charlie Thompson, and today I wanted to go over some of the basics to try to connect up the dots between the first chapters when we talked about energy from the sun and the current chapter when we're talking about weather. And in between, there's a whole bunch of connections that I think you'll enjoy the chapters if you understand those connections. So for this whole thing, I'm just going to use earth.nullschool.net. And for right now, we're just looking at wind patterns. So the longer the streak, the longer the white streak, the faster the wind speed. The shorter the streak, the slower the wind speed. Blue is the slowest wind speed, 2 kilometers, 2 kilometers. Notice the broad pattern of friction reducing wind speed over the land. 5, 8, 13. Let me put this in miles per hour so you're happier. 2 miles per hour. There you go. 2 miles per hour, 4 miles per hour. Over the ocean, though, 22, 23, 21. So the trade winds are zipping along because of lack of friction. There's a tropical storm out here in the middle of the Pacific, and 17. Let's see what the wind speed is. Nice. 71. Almost hurricane strength. 72. Probably getting really close to hurricane strength. And now that we've zoomed in a bit, hopefully you can see the ITCZ. These would be the southeast trades. These would be the northeast trades converging along the ITCZ. There's also a couple other cool things. There's the pattern of wind going through the passes and the mountains here. You can see it getting squeezed in. Last night, it was even more dramatic. So let's see if we can't. And that's 24 hours ago. That's yesterday, day before. Oh, that's weird. Okay, let's go back to today. Okay, we should be at today. There's that. You can see the wind whipping through there. And I also love looking at the pattern of wind with the islands of Hawaii. If we go back a day. Yeah, so if you are lucky enough... Oh, and the ITCZ is right over Kauai. That's fascinating. Absolutely fascinating. If I go back a bunch of days. Yeah. Okay, so things have shifted a bit. They're always shifting around. The ITCZ is slightly lower now. But you can see that the wind is coming out of roughly the northeast trade winds. And you can see it's hitting Hilo. If you've ever been to the Big Island, most people stay for tourism in Kona, which is on the dry side of the island. Hilo gets lots and lots of rain. Here's Kauai. The rainiest spot in the world is right there because it's in the trade winds. And one of the fun layers that I just realized, this 3 HPA, it's the 3-hour rainfall accumulation. And it's not really super impressive for today. What I was hoping it would show would be patterns of precip as a result of orographic effects, where the wind runs into the mountains. So let's go to today, turn you off. Oh, yeah, lots of rain there. And indeed here, where the wind is whipping into the land, it's getting lifted up. And so there's lots of rain there. These are fronts. We'll come back to them in a bit. Oh, here's another huge front. You can see very clearly as a result of the rainfall. Oh, man, you can see the ITCZ, this belt of rain, ITCZ. Oh, so this would be a combination then of ITCZ and orographic effects. And if I zoom in just a little bit more, hopefully the rain will be showing up on the windward side of these islands. It looks like it is up there. Can't really tell what's going on there, so maybe that wasn't great. India, that's what I wanted to find. So let's see if the monsoonal circulation is still going on. And indeed it is. You can see the wind coming down out of the south, driving north, running into the Himalayas, getting lifted up. So that's the 3-hour rainfall accumulation. Let's turn on the total precipitable water. This is humidity. This is water vapor in the atmosphere. The brighter blue it is. Oh, yeah. So we've got an enormous swirl around this tropical storm here off the Pacific. You can see there's an area of low pressure. So this would be a cold front right in here and a bit of a warm front. Warm air coming up. Here's cold air. Here's cold air, warm air coming up, getting lifted over the cold air, making a warm front. And here we've got cold air barreling along, running into this warm air. And then the cold air gets, or rather the cold air lifts up the warm air, pushes it up out of the way. In California, you can see it's just incredibly dry. 16 kilograms of water vapor down here, 70 kilograms of water vapor. Over here, 54 kilograms of water vapor per square meter. So 54 or 50 kilograms of water vapor, that's roughly 110 pounds of water vapor for every 3-foot square on the ground. So if you drew a 3-foot square on the ground here, and then weighed all of the water molecules in the atmosphere above that 3-foot square, all those water molecules would add up to 50 kilograms. Over California, well, over there, 3.7 kilograms and 2.2 pounds are a kilogram. So if you multiply it by 2.2, you get pounds. So like 20 pounds of water over California right now. And if I turn on the air pressure, this will explain exactly what's going on. So here's this low pressure around that storm. Here's the low pressure with the tropical storm. Here's, oh look, high pressure. The air is circling clockwise, coming out of the high pressure and then flowing towards the low pressure. So there's got to be slightly higher pressure here, higher pressure here, lower pressure there, really low pressure over there. If we zoom out just a bit more, you can see super low pressure right there. Yeah, high pressure in the middle of the Atlantic. Low pressure, that's a storm. Low pressure, that's a storm. Low pressure, that's a storm. That's a storm. That's a storm. That's a storm. We are still in the summer phase of the Asian monsoon with low pressure over Asia and high pressure over the ocean. So there's high pressure driving the wind to low pressure. Low pressure, that's interesting. Low pressure over the Sahara. All right, so what I'd like to do now is back up about a week. So if we're on today, 1, 2, in fact, I want to turn on temp, because that's 2. Right in here. That'll be perfect. Okay, so now we're looking at temperatures, and if I turn this off, and if I make it go to a different projection so we can see the whole world at once, this is showing temperature. So this is why I make a big deal out of the tropics. The tropics extend from the tip of Baja California, 23.5 degrees north, to 23.5 degrees south. So from 23.5 south to 23.5 north, those are the tropics. And you can see just from the colors, that is the warmest part of Earth. So because the sun migrates during December to March to June to September to December to March to June to September, because the sun goes back and forth across this region, they get way more energy, 2.5 times as much energy as the poles do. So every day there's more energy coming in the tropics than there is at the poles. Every day then, energy is migrating, moving from the tropics to the poles. In terms of temperature, we can see as soon as it loads, oh, swirls. Look, they're Rossby waves along the polar front. You can actually see the boundary layer in the polar front with the cold air coming out of the north and the warm air coming out of the tropics. If I turned on the winds, you'd see the trade winds going towards the equator. You'd see the westerlies coming out of the tropics, moving towards the poles, and then those weak polar easterlies pushing the cold air down where it runs into the warm air. So all along here, this is the polar front. Down here someplace is the polar front in the southern hemisphere. So there's a heat surplus in the tropics, and that heat surplus drives heat energy from the tropics towards the poles. One of the important ways that this happens is with the latent heat of condensation. So here you can see these big plumes of water vapor migrating from the tropics, where the water is evaporating, to the poles, where that water vapor condenses and releases heat energy. So another important consideration is this big string of moisture, this big stream of moisture. It's not just the gradual transfer of water vapor from the tropics to the poles. It's in these dramatic atmospheric rivers, and you can see these big plumes of moisture coming off the tropics being driven partially by the jet stream, partially by the surface winds. So in fact, what do we have? Surface, and we've got total precipitable water. If we were to go up to the jet stream and see what the winds are like there, you can see these big loops and curls in the jet stream are lining up pretty nicely with the loops and the swirls along the polar front. So yeah, that's pretty amazing, seeing the relationship. I mean, it's one thing to tell people about it, to tell you students, to tell students about it and say, hey, look, here's this picture showing the jet stream. It's this arrow, right? But the jet stream's a real, I don't want to say it's a living thing, but it sure as heck moves a lot. If we move forward a day, it's shifted. If we move forward another day, it's shifted again. So I want to go back 2 days. I want to turn off the wind, and I want to turn on the temperature, because there's temperature at the surface, because there's this outstanding example of a front. And I've kind of been struggling with fronts because they're incredibly important, but they're confusing. I know that there's a lot of information to take in at once with regards to front. So if we turn the wind speed on, we're going to have wind coming out of, we've got wind coming down out of the poles, the cold air coming down, and then we've got the warm air coming out of the tropics. And if we look at the temperatures, 58 degrees and 72 degrees. And if we look at, I don't want relative, well, let's look at relative humidity. So very dry, this cold, dry air down here, and then relatively moist, 80%, 93%, 97%. If we turn on the clouds, you'll see a band of clouds where the cold front is, where the cold air is coming down, running into the warm air, getting lifted up. Here's another front. Oh, and in fact, over the next day, you'll see as the front moves, so does the pattern of temperature. That you can see this cold air has shifted down. I back it up 3 hours, back it up another 3 hours, another 3 hours, another 3 hours. You can really see, especially if I get it to the right point, then we go forward again. Oh yeah, you can really see this band of cold air pushing into this blob of really warm air. So now if I drive it forward again, we go forward, we're going to see this cold front push this warm air out of the way. It's going to lift the warm air up. Oh, it's so dramatic. And if we turn on the clouds, there's going to be a band of clouds here. And there's going to be clouds up here where the warm air, this warm air is coming up. If I turn on the wind again, zoom in a little bit more. Yeah. So you've got cold air coming down, you've got warm air coming up. This is making a warm front where the warm air moves up on top of the cold air. And then over here, this is going to be a cold front caused by this cold air pushing along the ground, lifting up this warm air. And like I said, if I turn the clouds on, there's going to be clouds here. There's going to be clouds up here. Clouds, there's your cold front. There's your warm front. Now, if we turn on air pressure, there should be low pressure right in. Yep, low pressure, high pressure there, high pressure driving things clockwise, high pressure driving things clockwise, low pressure, everything's orbiting counterclockwise. So we've got wind, we've got total precipitable water, and looking at the total precipitable water for a while, I became really convinced how much of, and there you can see that front very clearly now with the total, the warm, moist water coming off the ocean and then the cold, dry air coming out of the tropics. By tomorrow, it should be pushed off even more. That's great. This storm looks like it's picking up strength. If we turn on the sea surface temperature, ocean, the sea surface temperature, don't need any animations. Sea surface temperature, You don't need to animate anything. Hello. Sea surface temperature. Yeah, so the region that storm is passing over, it's 83 degrees. If I turn the wind back on, air, wind. Yeah, so there's the storm. Now if we go back to ocean and sea surface temperature, yeah, 83 degrees water. And as it moves along, you can see that the water stays pretty warm, unless it diverts north and tries to go up the west coast of California, in which case it's going to run into this cold water and it's going to die very quickly. Hurricanes cruising across in the tropics are going to go over much, much, much warmer water. Hurricanes traveling, or by the time they're over here, they'd be typhoons. 87 degree water, 87 degree water, 85. So still incredibly warm water, and you can see very nicely the pattern of clockwise rotation. Ah, yes. What would happen if Earth rotated backwards? Well, the oceans would rotate the other way, so we'd have a cold current, a warm current coming up. A warm current coming up from the south off of California. The winds would be going the other way, so we'd have warm currents. We would have the similar climate to Florida. Many of you said that on the test, although I suspect it's just off of that one article that you found after you Googled, what would happen if Earth traveled the other way? So the answer is warm current and humid summers and climate similar to the southeast United States. So we've got the Gulf Stream, we've got the Japan current, we've got the cold California current, we've got air, we've got winds, we have fronts. In fact, looking at weather maps, fronts always look really crisp and clean, and in reality, they often look messy. They're often hard to look at and go, what am I actually seeing? Except in like this is a really good example just because it's so obvious. One of the big clues is that the wind direction changes 90 degrees. So like here the wind's coming out of the west, here the wind's coming out of the south. If we turn on the temperature again, there's going to be a big difference on either side. 72 degrees, 64 degrees. The relative humidity is going to be different. 67%, 95%. Total precipitable water, dry, cold air, warm, moist air. Except in the tropics, right? This is a mid-latitude cyclone or mid-latitude wave cyclone. So it's made up of cold air combining with warm air. And in the tropics, it's all warm air. There are no fronts. It's just a big blob of rotating warm air. And then hopefully over time we'll get more coming across from Africa. Like that looks like it could develop into one. Day after tomorrow. 2 days forward. 3 days forward. Nah, looks like it's kind of fizzling. Although there's something going on here. Oh, that fizzled too. Oh, and our little storm looks like it could be trying to make a trip to go over to the islands in Hawaii. That's interesting. Anyway, to summarize and stop just playing around with this. Temp. No animation. Because Earth is curved, different latitudes get different amounts of energy on the same day. This builds up a surplus of heat energy in the tropics. There's a heat deficit or heat energy deficit at the poles. So heat travels from the equator to the poles. One of the ways it does that is wind currents. The westerlies bring water vapor in the form of latent and latent heat in the water vapor because the air itself isn't hot. It's just a gas because it's a phase change. And when the warm, moist air moves up to the poles, it gets cold. And as the water condenses, it releases that heat. So all of this circulation, and if we turn on the ocean, yeah, the ocean currents are always a trip. They're always a trip because they always look so chaotic and confused. Although you can see the equatorial current, you can see the Japan current, the warm current. You can see the Gulf Stream, the warm current there. but the same pattern of heat energy moving along the equator and then moving up the east coast of continents, and then that heat energy getting dumped out at the poles, and then cold water coming down the west coast and then returning along the equator. So if we go back to total precipitable water, and if I back it up, can I back it up a month? Let's back it up 2 months and see what happens. So here's 2 months ago. And if we go forward a day at a time, you'll actually see the pattern, the migration of the water vapor moving westward across the equator with trade winds pushing everything across. And then you'll see the westerlies moving these big plumes of moisture, these storms, these mid-latitude cyclone. There's a very strong cold front. There's a really nice warm front. And you'll see the westerlies migrating eastward, and you'll see and I just, look at how dry everything is. Well, because it's the poles. So looking at those of you who are in lab and have been looking at the maximum specific humidity charts, you know when the air gets cold, there's virtually no water holding capacity whatsoever. As the air warms up every 10 Celsius degrees, the amount of water vapor that can be present doubles. So when you get down to really cold temperatures, like here in the Antarctic, how cold are you, Antarctic? -11, 32, 20. So very, very cold. Let's go back to total precipitable water and keep running things forward. So you'll see these big plumes, and I realized, it's these dramatic plumes, these atmospheric rivers, and we'll talk about them later. Atmospheric river events turn out to be very important bringing precip to California, that these plumes of water vapor coming out of the tropics can actually carry more water than the Mississippi. So enormous amounts of water vapor. And again, looking just at the total precipitable water, you can really see the distribution of the world's deserts. So here, the Atacama, Southern Africa, Australia. Most of Australia is a desert. The west coast of California. So the desert's really obvious if you're looking at the water vapor. And then moving things forward again, you can see everything start to slide across the equator. I would play around with the earth.nullschool.net and look for these atmospheric rivers. I would look for tropical storms. I would look for patterns of low pressure swirling clockwise in the southern hemisphere, low pressure swirling counterclockwise in the northern hemisphere. I'd play around with the projections, like the orographic is the Earth from space. That's really nice for seeing part of Earth, but if you want to see the whole planet, I would recommend the Patterson projection. It's a relatively low distortion projection. The conic equidistant is a good projection if you're zooming in on the United States. Relatively distortion free if you want to just set up the US and observe high pressure and low pressure and low pressure. Nope, that's high pressure. High pressure, low pressure, high pressure, low pressure. And then enjoy all of that moisture coming out of the tropics. The 3 HPA, the 3-hour precipitation accumulation, shows you, like I said, where it's been raining. Lots of rain there. Rain over there, we're not getting any, although we might be getting some sometime soon. And again, if we go to today, again, with the 3-hour precipitation accumulation, you can really see the cold fronts. Really see the cold fronts. So let me back that up a couple days to see that front when it was over us, or over the East Coast rather. So yeah, so now you can see the cold front, you can see the warm front, you can see another cold front here with the cold air coming down. If we turn on the temps, yep, warm on this side, cold on that side. If we turn on the relative humidity, it's going to be moist on the warm side. It's going to be dry on the cold side. Oh, CAPE I haven't played around with. That's energy for convection. convective available potential energy. So that's the places that you'd expect to see more thunderstorms. And indeed, right along the bottom of that cold front, high CAPE values indicating lots of energy to make thunderstorms. And then if we go back to total precipitable water, again, it's humid on the warm air side. Total cloud water, where the clouds are, there ought to be a belt of clouds where the cold air is shoving up this warm air, and then that warm air, as it travels up, runs into the cold air and gets lifted up. So that's another front. Anyway, I think that's probably everything that's good to cover at this point. Otherwise, I'm just going to keep going over the same ground again and again because I find it so absolutely fascinating. Ooh. Yeah. And for those of you that noticed and commented on the discussion questions, wow, Earth, those winds are actually not just local. There's entire global patterns. And especially if we get up into the jet stream, you can see the polar jet, you can see the subtropical jet and the polar jet, the southern hemisphere and the northern hemisphere. It looks like they've sort of fused together. Here's an example of 200 mile an hour wind. And then if we compare that again to surface wind, sometimes you can make out, like here, I would say, sure, that's the northeast trades. Sure, those are the southeast trades. These are definitely the southeast trades. Northeast trades over here. But the westerlies, well, look at that and go, well, there's some of the westerlies because it's just an average, right? It doesn't mean that the wind is always blowing out of the west. And then here, yeah, those are the westerlies. And then those are the southeast trades caused by this high pressure. Oh, yeah, I started doing it again. I got lost. Sorry. I'm going to bail. That's it for this quick video on enjoy some nature. Play around with earth.nullschool.net. If you mouse over the tooltips, it'll tell you at least what the words are. If you want more information, you could go to the About page. That's got some good stuff. And you could show up and ask me what the heck he's talking about. I would love to discuss anything about earth.nullschool.net. It's a phenomenal resource. It's fantastic. Anyway, hope you enjoy it. If you have any questions, please let me know. I'd love to talk about weather. That's it.